Welcome to this 11th presentation of algebraic structures. I said we will take up alternating group on 4 symbols again, but let's hold on to that a little bit. What we are going to do is we are going to look at isomorphisms now, okay? And a reason to look at that would be that there are several different looking groups who are same in the structure. For example, if I take this additive group of Z4, that is the integer modulo 4s, and this and there is another group of 4 elements in which we have the operation as the multiplication of complex numbers, okay? And these are the fourth roots of unity. And we shall see that they all have almost same properties as far as the group theoretic or the group structure properties are concerned. For example, so let's again look at them. And remember I said that I would stop putting bars on these numbers. Once I say addition modulo 4, it's clear that these are, these are integers modulo 4, okay? So you can see this group is generated by, say, 1, because we have 1. Then 1 square is 1 plus 1, that is 2. 1 cube along the same lines is 1 plus 1 plus 1, that is 3. And 1 to the 4 is actually going to be 0. And then 1 to the 5 will be back to 1, and then the cycle starts again. And what we called this was a cyclic group, right? And in the case of these guys, what we have is, if you look at this is a cosine of pi over 2 plus I sine pi over 2. So that's going to be 0 plus 1i, that is I. And let me write the rest and bring it back to you. So here, based on the Euler's formula, okay, we have, based on the Euler's formula, we got the e to the 2 pi over 2, which is I square, that is -1. Then e to the 3 pi I over 2, that will be -I. And actually this is I cubed, and then e to the 2 pi I over 2 is I to the 4th power, which is just 1, right? So how did we start? We start at I, right? And when we take I square, we get here to -1, right? -1, 0. Then when we take I cubed, we got to 0, -1, and I to the 4 just becomes 1. And then it just repeats. So the cycle just repeats, and it does look like a cycle. So what we have is that both of these are cyclic groups, okay? So what we can do is, even though here the operation is addition, here the operation is multiplication of complex numbers, we can define a correspondence between these two groups and see that all the properties of the elements are preserved under that correspondence. So what we are going to do is that we are going to define a correspondence between these two, and a natural way to look at that would be, you can see that this group is generated by 1, and this group, like 1 is one of the generators actually, and this group is generated by e to the pi I over 2. Okay, so what we can do is that we can take a map, and let's call map say phi, all right, okay, from, instead of Z4, let's call it 1. We know it will still have 4 elements, okay, 2, these, and what we are going to do is we are going to take the phi of 1 as simply e to the power 2 pi I over 2, which is a generator here, right? And then when we have to get pi 2, all right, so who is pi 2? Pi 2 is the second power on 1. So we shall take the second power on this from here and take the map as this, okay? And then when we go to pi 3, okay, or rather phi 3, I'm sorry, I've been mispronouncing, then who that will be, that the who that can be, we are just proposing, okay, that is this one. This is the third power on the generator that we assign to the generator 1. And then at the end, when we, let me just write the end below here, that is when we look at phi of 0, okay, then what we have, that's the fourth power on 1. So this will be fourth power here, or in simple terms, phi of 0 would be this, and this will look much simpler as 1. Okay, so in this manner, what we have done is, you can see one thing for sure, that I have defined a map from these 4 elements to these 4 elements, okay, and everything goes to a distinct destination, and everything here is covered by an element over here. So we see this here, that phi is a 1-1 onto map, okay, onto map. And in addition, if you take the product of any two elements, or say if you combine any two elements, for instance, let's do this here. By the way, here there is a typo, okay, so I corrected that typo. Notice this, if I look at this, that phi of, that who phi of 1 plus 2 is, okay, then you can see that will be who phi of 3, right? And phi of 3 is how much? That's simply this element here, okay? And the way we constructed the definition, even if we do this, that is add the images separately, okay, that is, we got this here, then we got this here, okay, then what we will have, pi of 1 is this, right, and that of 2 is this right here, and the operation here is multiplication of complex numbers. So what will happen is these two powers will add, and we will simply get e to the 3 pi I over 2, right? So, and you can do that with any pair of elements. You shall see that the relation is satisfied. So we have a 1-1 onto map. Okay, so we got 1-1 onto map, okay, which preserves the operation, or respects the operation, or you know, you can say it in many ways. And if we write it symbolically, what we have is this. So now in general terms, if we have two groups, G1 and G2, and the operation or binary operation in the first group, we are calling it O1, and that in the second group is O2, Now, a map from G1 to G2 is called an isomorphism if we need two conditions here. One is that phi is 1 onto or a bijection or is a bijection. And the second condition is that if we take two elements, A and B in G1, then we know that their product or if we look at the value when we combine them via binary operation in G1, that will be in G1. Okay. Now the condition that we need is this, that if I apply this map phi on this element of G, of course I will get, G means G1 here, sorry. So we are going to get an element in G2, right? Excuse me. Now this element would be actually the images of A and B under phi, all right, combined with this operation, that is this binary operation in G2, okay? So it has to satisfy this condition. Let me see if it fits in our recording screen. Yes, it almost does, or that's okay. You know what I mean. All right. So let's take an example here of an isomorphism. So what I'm going to do is that I'm going to take the group of real numbers with respect to addition. Okay. And taking the group of positive real numbers with respect to multiplication. Okay. So here I have, and notice this, this these positive real numbers, they are a subset of real numbers, but still we have a bijection between the two, and one bijection or one onto map. I am going to show you recall for you already. You may remember this famous map are, from R to positive reals, okay, which is given by, okay, f of say x, we take it to be the natural exponential function. We can take it any exponential function, but let's stick to the natural exponential function. Okay, so you know that this is a 1 onto map, right? Because if e to the x, okay, equals, or e to the x1 equals e to the x2, then you may recall from your Algebra 2 course that it was, it passed the horizontal line test. That's why it was 1, 1. Or you may take logarithms of both the sides, okay? And then what will happen? That will imply that e to ln of, because logarithm is a 1, 1 function, or let's just assume from our real analysis that it is a 1, 1 function. That would be the best way to do that. All right. And then if we take any y in the set of positive real numbers, okay, then what happens is, so for any y in the set of positive real numbers, if we take x to be ln of y, then what happens? E to the power, or rather f of e to the power x, f of x, that is f of e to the power ln of y, right? That equals, or no, not e to the power ln of y, I'm not paying attention to myself, sorry about that, is f of ln y, that is e to the power ln y, that will become y. So the map is onto, right? And at the same time, you can see that if you look at f of, say, x plus y, okay, so what will that be? That will be e to the power x plus y, and that with the properties of exponentials, what we have is you can multiply if we have sum of two powers as exponential, or in other words, when we multiply two powers, we got the sum and vice versa. So this becomes fx times fy, right? Okay, so in this manner, the group of real numbers and the group of positive real numbers, they are isomorphic to each other, okay? And this isomorphism, especially because of being 1 onto and having this property, okay, that is, it satisfies many, many nice conditions. For instance, 1 second, let me just bring in this notation that we have a phi from G1 to G2, all right, and the operations are O1 and O2. So in this case, because of this property, what we have is if, say, E1 is the identity in, okay, say E1 is the identity in G1, okay, then what happens is, then phi of E1, that is, identity will be carried to identity. Okay, so here, this is going to be what? Let's call, if we call it E2, then E2 is the identity in the identity in G2. I mean, I assumed actually in advance that E2 is identity in G2. Let me be careful not to make such slips in the future. So, so what we have to show is, so to show that that E2 times, okay, E2 times Y equals Y for any y in G2, right? Okay, that's what we have to show. So for any y in G2, so let's go with any y in G2. All right. So for any y in G2, okay, I'm going to be a little formal now, okay, because this guy phi is onto, all right, because phi is onto, we have an x in G1, right? So we have an x in G1 such that, okay, such that, sorry, such that phi of x equals y, right? Such that phi of x equals y. So now what happens is that we have, one moment here, I did not type it properly, sorry about that. Okay, so now what you have is that E1 times x, so here is my E1, okay, and times means the times in G1, okay, all right, so E1 times x is x, okay, all right, then this will imply, because phi is a map, okay, that's how we took it. So this implies that this equals phi E1 O1x equals what? Phi of x, right? Okay, so phi of x. And now what does this give us? This gives us that now we have the condition that it respects the operations, right? So we got this time when we go to the image set, right? So what do we get there? That this times phi of E1, okay? Phi of E1 equals who? Equals phi of x here, right? And how much is phi of x? It's right here, it's y, right? So what you got then is this, that phi of x, times phi of E1 is y with the operation in G2, and phi of x is what? That's a y, right? Rather, that is y, and we chose y arbitrarily, right? So who this will have to be, because the identity is unique in a group. So therefore, we must have, so therefore we have this element equal to identity in the group 2. Okay, so what happens is an isomorphism will carry identity to identity, right? And at the same time, along the same lines, let's just do this. That is, if we have this, so if phi of x is y, okay, then what we can see is that it carries inverse to inverse. So for example, if we apply phi on x inverse, then what we will end up getting is the y inverse, and we can see it slightly easier than before. So say we have this is what we have to show. So you can, I mean, you know this, that x times this thing, or rather, let's just write it in that order. It, or 1 second, I don't know why I'm again stammering so much. So we know this, x inverse, okay? And let me just be formal for a few more minutes, okay? This equals how much? The identity element in G1, right? Okay, so this is what we have. Now what we can do is, let's apply this phi on this product, okay? So we got phi, and then we will apply this on this product. So phi of x composed with x inverse will be what again? Phi of E1, right? E1, okay? So what that gives us is, that gives us that phi of x, okay, I'm sorry, that means that equals okay, so that gives us that phi of x, and then operation will be the operation in the group 2, okay? Well, let's bring this implication here, okay? And then that will be what? Phi of x inverse, right? So phi of x inverse, and that's going to be how much? Phi E1, we know that is E2, that is the identity in G2. So we got this here. Now, what did we begin with? That our phi x is y. So we got y times phi x inverse equals E2. And so what does this mean? This means that this is the inverse of y, because inverse of an element in a group is unique. So that shows what to you right away, that y inverse equals how much? Phi of x inverse if, oh, sorry, not that, okay, if, or rather, we just proved this statement, okay? All right, that is phi x equals y implies that y inverse is the image of x inverse, okay? So let's take a quick illustration of this through an example that we just did. So remember we did this example where we defined where we have an isomorphism from R with respect to addition to positive reals with respect to multiplication defined by this. So if you look at this, f of 0, where 0 is what? 0 is the identity in the additive group of real numbers. So what is the image? The image is e to the 0, right? And that becomes what? 1. And 1 is the identity in the set of positive real numbers with respect to multiplication. And that's all we are considering right now, even if we take non-zero real numbers, still 1 is the identity, but let me not stretch it. Okay, so here we see identity goes to identity. Now, for the preservation of the inverse, you can see if we take any positive real number y, okay, since this is a bijective map, we have an x such that fx is y, and which by definition means e to the x is y. Now, if we look at the inverse of y in the set of positive real numbers with respect to multiplication, then who is that? That is simply the reciprocal of y, and that is going to be who? The multiplicative inverse of e to the x, or in other words, -1 power on e to the x as we take it in the sense of our real numbers. So this is e to the negative x. And who is that? That is f of negative x. So what we have is that inverse of any element here, okay, is the image of the corresponding pre-image in this side, or actually, so what we have is y inverse is equal to f of the inverse x, where fx equals what? Or rather, in other words, fx equals y implies that y inverse is the image of the inverse of x, okay? So anyways, we saw that we have bijection, sorry, an isomorphism between R and R plus. Let's look at that, just like graphically, because just as a review of our algebra 2. So what we have here is that this fx equals e to the x. This gives us an isomorphism between the set of real numbers to the positive set of real numbers, right? So let's try to see if we can do this. That is whether, let me change it. So question is that can I do this, that obtain an isomorphism, okay, between, let me remove this here, okay, between, and here I'm just going to, write it in red color, okay, so between the set of real numbers with addition, okay, to, now this time the set of non-zero real numbers with respect to multiplication, that is, all I have is 0 is kicked out, okay, so we want to know if we can have an isomorphism between those two, okay, so let's look for it. So sorry, this is multiplication, and this is of course the set of non-zero real numbers, and we are looking for a phi such that phi from R to R star is an isomorphism. And notice one thing, that this guy 0 is already assigned to 1 if phi is an isomorphism between these two. Okay, so why don't we concentrate on -1 now? And that's where we see a trouble sets. Okay, and of course I know this reasoning from before, so I'll just try to make it as natural as possible. So as I said, we are focusing on -1, all right, and 0 cannot come to -1 just because under isomorphism, 0 and 1, they have to correspond to each other, and we are looking at the multiplicative group of non-zero real numbers, right? So what we have to have is this, that we have to have NA, which is not 0 in R, right? Such that, phi, that's what we are taking as our map, such that phi of A is -1, right? Now, if you look at phi of A, I can split phi of A as A over 2 plus A over 2. All right. So if you look at this, then what you would find, that the image will be phi A over 2 times phi over 2, right? Because of the operation preserving property, right? And where is this element, phi of A over 2, that lives in the set of positive real numbers? So these two multiplied becomes what? Phi of A over 2 is square, and that equals -1. And we know that this isn't possible, right? Okay, so what happens is that we will not have no isomorphism phi between the set of positive real numbers and the set of set of real numbers with addition to set of non-zero real numbers with multiplications. Okay, so we cannot find any such isomorphism. Okay, now let's take up the very first theorem of this chapter from the book, that if G1 and G2, if they're isomorphic, then G2 to G1, we will have an isomorphism F inverse. Their cardinalities are the same. If one of them is abelian, then the other one is abelian. If one is, it says if G1 is cyclic, then G2 is cyclic, but by the inverse, we will have vice versa as well. Okay, that if one is cyclic, then the other one is also cyclic. And if one has a subgroup of order n, then the other one also has a subgroup of order n. So the book does a good job of proving these three and leaves parts D and E for us to prove. So let's just go ahead and give that a try. So what we have is that we have an isomorphism between G1 and G2, and what we have to show is that if G1 is cyclic, okay, so G1 is cyclic implies that G2 is also cyclic. And what we are going to aim for is this, that if G1 is generated by an element A, then this is what we will try to do, which looks quite natural, that G2 should be generated by f of A. All right. And of course, A is an element in G1, and f of A is of course an element of G2. Okay. So G1 is generated by A means what? that any element in G1 is an integer power on A, right? So to show that G2 is generated by FA, let's try this first, that f of a to the power n, that is the same as the nth power on f of a. Okay, so you know this, if I have f of a to the power 2, that's no big deal because this is f of a. Now I'm not distinguishing between the symbols for the two groups. Now this is a property that it respects the operations. So we have this as f of a square, and we can continue in this manner. But just to fulfill the logical requirement, let's go by induction. And we know one thing for sure, that f of a to the 0 is f of e in the group 1, and that will go to e2, and e2 of course is the power 0 on any element. What I wrote here is the 0 power on f of a. So we got that, and we got that, and f of a to the power 1 of course is fa, and that is fa to the power 1. So it is true for n equals 1. So let's just go ahead and first show that f of a to the power n is fa to the power n for any positive integer. I'm going back from typing to writing by hand, and I hope it is tolerable for you all. So that's what we are going to look for. Okay, so what we have is, so notice this here. So we know that it is true for n equals 1. And remember this, we are not restricted to positive integers here. Okay, but we will take up negative integers in a moment. Okay, so for n equals 1, we saw that it is true now. So let it be true for n equals k. That means what? F of a to the power k would be the kth power of fa, right? Now, if we take f of a to the power k plus 1, then that is going to be f of a to the power k, just a second, f of a to the power k times a, right, which can be written as f of a to the power k times f of a. And let me just do some erasing and do it in a different place. Okay, so one moment. So on the previous slide, what we were doing was that if this is an isomorphism, then we are going to prove this for positive integers n. For 0, we had already seen that it was true. We saw that it is true for n equals 1, even n equals 2, we saw it true for. So now if we assume it true for a positive integer k, that is f of a to the power k is the kth power of f of a, then what happens is, if we look at the image of a to the k plus 1, we want to show that it holds true on this as well. So that is, we can split this as a to the k times a. That will be f of a to the k times f of a. And remember this right here from our inductive assumption, what we have is that f of a to the power k is the k power on f of a, then times f of a. So what we find is that f of k a to the f of a to the power k plus 1, if we multiply these two, will again be the power k plus 1 on f of a. So this statement is true for every positive integer and actually every non-negative integer where because we saw it true for n equals 0 as well. So that is, we have this property true for n greater than or equal to 0. Now let's let n be less than 0. Less than 0 means let's let n be negative m, where m is what? M is a positive integer. Okay, I'm not mentioning it, but we are taking m as positive integer. So now what happens is this, that is, if we did this, if we took a to the m times a to the negative m, what that will be? That will be the identity in the group 1. So what we have is f of a to the m times a to the negative m equals f of e1, right? Which means f of a to the m times f of a to the negative m is e2. All right. Now, pay attention to this portion here. M is a positive integer, right? So what will this do? Let's come up here. That f of a to the m will become the power m, on f of a, right? And then we got f of a to the negative m equals e2, or in other words, f of a to the negative m, if we take it to the other side, okay, then that will be f of a to the power negative m. Now remember, negative m is who? That's n. That's what we had chosen. Okay, so what does this give us? This gives us that f of a to the negative m means a to the n. That is the same as f of a whole thing to the power n, even for a negative integer. So what we have established is this, that is f of a to the power n, sorry about that, that f of a to the power n equals the f of a to the power n for all integers n. Okay, and now rest will be very simple, hopefully. Now, before going down to the next slate, I see a problem here that I wrote a phi, and the reason being this, that I had like phi as my main map. Suddenly, for whatever reason, I did that, so I did that. So make sure that we fix this mistake here, that I'm taking f here, so I should keep this as f. All right, so that was a typo and I went along with, and we are not together, so nobody could interrupt me, which generally happens when I lectured before in a setting like this, especially for proofs. So anyways, let me go to the new slate, and this time I will not mix up between the symbols, and hope I have been forgiven. All right. So we have an isomorphism, and we showed that for any a, if I take the image of nth power of a or f of a to the n is the nth power of f of a. And what we had started to show was that if G1 is a cyclic group, say generated by an element A, then G2 will also be a cyclic group, and that will be generated by f of A. This is what we want to show now. So all that we have to show is what? Take any y in G2, we would like to show that y is an integral power of f of A. So if I take any y in G2, that means we have an x in G1 such that f of x is y, right? Because our map is an ontomap, right? Okay. Now, since X is a cyclic group, sorry, since G1 is cyclic, okay, so X belongs to the cyclic group generated by A. So X equals what? A to the power N for some N, right? So then what happens is Y, which is f of X, is f of A to the N, okay, because x is a to the n, and this is f of a to the power n, because we established that, right? So y is how much? F of a to the power n, and that means that any element of G2 can be written as a power on f of a, and we can go on to show that G2 is a cyclic group generated by f of A. Now, what we will do is this, that the property number 5, or the property number E, let me take you there. So remember this, that in this theorem, the book wanted us to do the properties, approve the properties D and E. So D we just finished, and what we will do is that we will take up E in the next presentation. And I'm not just going to be like trying to finish each topic in one presentation, and I'm making them between 45 to 50 minutes. So I'll just make I'll just title the next presentation as Isomorphism 2. Okay, so we shall take this one and the other material that we want to go over isomorphism in the next presentation. All right, so see you then. Thank you.